This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you something different. As you can see, there is a visual design in front of you, and I got the task that I should translate this visual design into a working PCB badge. So what I got is basically this PDF and the source code and just some information about this project and the ideas about the project. And I have to make this into a working PCB. So this page in front of you shows you the final design. As you can see, the PCB is planned to be in black color, and then most of the text and the graphical elements are in gold. And then here in the center you can see that there is a bunch of dates between 2014 and 2025, and these blue rectangles symbolize LEDs. And the reason behind this design is that this is a badge for PCBWay's 11th anniversary. And then the author of this design decided to do this design because he wanted to celebrate PCBWay's 11th anniversary with this design. So there are several pages in this PDF. This is the overall design. And then I got the layer for the golden design, and this will be on the front mask of the PCB. And then this will be the white silk screen. So all these white things will be the silk screen. And then I also got some very interesting, let's say, layout here. So we have the LEDs, and then we have the resistors. So it will look like this. And then this is the final connection diagram. And about this diagram, I want to explain a bit more because it looks a bit funny. So as you can see on this design, we have a 3-volt battery here, and then we have some kind of microcontroller which is labeled as ATtiny, and then we have the resistors here, the LEDs here without any marking for the polarity, and then we have a switch. So there are several design issues with this because this is just some kind of sketch, I believe. So I will walk you through all these design errors, and then I will obviously show you how to solve these. I think this is just a visual design, and there are not really much, let's say, electrical engineering knowledge behind it, because first and foremost we have the positive pole of this battery holder, and then that goes to the ground connection of the ATtiny microcontroller, which is already a huge mistake because, yeah, you cannot complete the circuit this way. And then if we still look at the, let's say, power supply connections, we can also see that there's a VCC connection without any terminal. So this supposed to go to the 3-volt battery's positive terminal, but it does not go anywhere, so there is no connection between these two, let's say, pins. And then the negative pole of the battery, that goes through the switch, and then it goes to the LEDs, and then through the resistors, which are in series with the corresponding LED, and then it goes to the individual pins of the ATtiny microcontroller. So to see and clarify things a bit better, you can see that, for example, the numbering of this microchip is also a bit funny, because the top left corner is numbered as 5. But actually, this is not super bad, but it's a bit misleading, because typically this should be pin number 1, and then 2, 3, and 4. But that numbering that I drew here is actually the physical numbering of the pins. And what you see here as 5, 3, 4, G and D, and so on, those are the port numbers. So the numbering is kind of correct here, but it's a bit misleading. So we have to consider that when I'm showing you the KiCad design as well. But if we look closer, and if we know a little bit about the ATtiny microcontrollers, especially, let's say, assume that this is the ATtiny 85 microcontroller, then there will be one big issue with the pin 1 or pin 5, because actually this is the reset pin. And the problem with that is that when you program the microcontroller, and if you don't do anything, you just upload the program, then this pin cannot be used. So actually this R11 and the corresponding LED cannot be used because that is the reset pin. So what I will do when I redesign this is that I add this pin to another bunch of LEDs just so that we can drive it. And the problem, or not necessarily problem, but let's say the problem for beginner users is that if you want to use this pin as a GPIO pin, you actually have to reprogram one of the fuses in the microcontroller. So then this pin becomes a valid GPIO pin instead of being the reset pin. But then we lose the reset functionality of the pin, and therefore we will not be able to reprogram the microcontroller in the traditional way throughout the SPI pins. So then instead we have to use the so-called HVSP, or high voltage serial programming, which is in a nutshell applies 12 volt voltage on the reset pin, and that will reset or set the microcontroller into programming mode again. Then also regarding this circuit is that, let's say we assume that the VCC is connected correctly and the ground and the battery is connected correctly. Then we can actually see that the author wanted to drive the LEDs through the GPIO pins. So I'm just drawing the sketch here on this line that you can see here. Then this should be the positive side, and then this should be the negative side, and then so on and so on. So each GPIO pin is the high pin which is driving the LED, and then the switch should cut the ground of these. So this is wrong, because actually when you would connect the battery and you just cut the ground with the switch, then probably the ground would be still connected to the battery, and therefore the chip would be still under power, and that's not the best let's say practice. So what I would do is that I would sync the current with the 80 tiny pins. So how it would look like is that we have the 80 tiny. Now I'm just drawing a very simple sketch, and then eventually I would use the 3 volt as the power supply, and then I would drive the LED. So I just try to draw it here, and then I would put the resistor here, and then eventually I would close the circuit with the GPIO pin. And then of course here would be the ground, and then here would be the VCC, so the 3 volt again. And then this is how I will do it. So I will do a so-called high side driving of the LEDs. So each LED will be driven directly from the 3 volt, and I will rewire everything. So then the switch will cut the 3 volt power both towards the LEDs and towards the 80 tiny microcontroller. So then it's saving power. And regarding the LEDs, I'm going to use red LEDs. So if we know that we are using red LEDs, we know that their forward voltage is 1.9 volt. So we can write it down that that is 1.9 volt. And then we have the supply voltage, which is 3 volt, because that is the battery. So then actually we can calculate the necessary resistor if we know which current we want to use to drive the LED. And that is nothing else, just this formula that let's say we say I LED is 2 milliamps. That is like a typical current, and I'm considering that this battery cannot push a lot of current out. We have to consider that we have multiple LEDs, 11 in total, and we have to also consider that the 80 tiny microcontroller cannot sink infinite amount of current per GPIO pin, which is 40 milliamps, but we want to be very conservative first of all, and we also want to save a lot of power because we want to operate this circuit for a long time. So then if we want to assume the resistor for driving the LED, so let's say RD, then that is nothing else that Vs minus Vf divided by I LED. So this is just simply Ohm's law. And then this will be at the end 1.1 volt divided by 2 milliamps. And then this should be 550 ohms. So if I want to drive my red LEDs with 2 milliampere current, then I have to choose 550 ohm resistors. If you look at the standard resistor series, then the closest one will be actually 560 ohms, and that will provide roughly 1.9 milliamps. Or if you want to be even more conservative, then you can use the next one, which is slightly higher, and that can be the 680 ohm resistor, which will give us roughly 1.6 milliamps, and that will be still high enough brightness for the LEDs. So by knowing all of these things, we can go to KiCad and we can actually design this circuit with the correct connections and with the correct layout. So I'm not going to bore you with all the details how I put together everything, so I already show you the final design. But if we start with the power supply, then what we have here is that we have a battery cell, and then of course the negative goes to the ground and the positive is switched by a two-way switch, and it is switching towards the VCC rail. So when the switch is switched between the 1 and 2 position, like you can see it here, then the battery cell's positive pole is connected to the VCC rail, so the battery is part of the circuit. But when it is switched between 3 and 2, then the positive side of the battery is cut off from the VCC, so therefore we don't have any voltage, and therefore we don't drive anything, so the circuit is off. And regarding the microcontroller, so as I said, I get rid of the PB5 or the reset pin, so I just put a no connect symbol there, and then I put labels to each of these GPIO pins, and I marked the labels according to the pin numbering. So we have pin 3, 2, 7, 6, and 5. And then obviously the VCC and the ground is connected, so then the 80 tiny is inside the circuit as it should be. And then we have the VCC rail, so I did a big rail like this, and then you can see that each LEDs are driven by this VCC, and then each LED or group of LEDs, you can see them in the blue boxes, they are connected to their corresponding, let's say, driving resistors, and I picked them to be 560 ohms, so they will be a bit brighter at 1.9 milliamps. And then each of these resistors are connected to the corresponding pin outputs. And then when it comes to components, so if I open the LED, then I assigned 0402 LEDs. So they are a bit tiny, but you will see it later on when I show you the design that I had to choose this because otherwise the badge would be ridiculously large. So I wanted to make it as a badge and not as a large disk. So I had to keep the sizes small. Therefore, I selected the footprint to be 0402. But the resistor can be a bit larger, so actually this will be easy to manually solder even, because 0603 is a relatively easy to handle size. And then when it comes to the switch, that's just a simple switch. There is nothing extraordinary about this, and they are available wherever you buy them, Mouser, DigiKey, and so on. So they are easy to find. And then the battery cell is actually not the battery cell itself, but the footprint of it is just a specific battery holder that you can also find in any large supplier. And then the 80 tiny is an 80 tiny 85, and I picked the SMD version of it, so it will be more nicer on the board because it will be flatter. And since I don't want to mess with the, let's say, looks of the board, I don't want to have any through the hole components, therefore I also picked the SMD version of it. So with this the circuit is ready and we have to implement it in a PCB. So we can move to the PCB design module of KiCad. And then obviously, again, I have already done this, but I will tell you how to make the graphics scene as you can see it in the 3D render, like this. So I'm showing you the final result. So you can see the 0402 LEDs, they are there. You might also see that each pad has vias, because that's how we reach the circuit on the back side. And you can see that the text and the graphics is nice and shiny because it is made with exposed copper, or actually it will be gold coating. And you can also see the white silk screen, which is the graphics. And then on the back side, I have all the resistors laid out as they should be, and then they go to the corresponding LEDs. We have the switch at the bottom of the board. We have the battery holder, the ATtiny chip, and then this is the name of the designer or his Instagram account. So I put it here because he provided the graphical design. But then I also felt like I want to mention that actually I implemented this into a working circuit. So that's what I put here. And to be extra careful, I marked the polarity of the battery. It's not like it plays any role here, because based on the holder here, it is already given that the bottom will become the negative pole, and whatever is connected to the top side will be the positive pole, and everything is wired accordingly. And as usual, I have curved traces because I like them, so I think, yeah, the circuit looks quite okay. But if we go back to the front side, then we can see that we have this golden design with the text and the numbers, the dates, and PCBWay's logo. And we also have this white background, which together makes the badge to look nice. I want to show you how to import this from, for example, the PDF that we got. So we have GIMP, and actually that's a fantastic software because it can open PDF pages as images. So what you can do is that we go to File and Open as Layers. So I open the PDF and we can see the individual pages. And I will import everything and later on sort them out. But one thing which is very important is to import it as a highest possible resolution image, because we will need smooth edges in the KiCad design. So actually I will change the width to 2000, and since the aspect ratio is fixed, then the height also becomes 2000. So this is a large enough resolution for the image that we want to use later on. So I import everything. And then now you can see that actually our image is a bit misaligned. So the first thing I do is that I align my layer somewhere here, so I can see the layer in roughly the center. Then I actually have a bunch of layers which I don't need. For example, this, I don't need this, and I don't need this either. So I just have this layer and then this layer. As I said, this layer will be the silk screen, and this layer will be the front mask. So we have this layer here, and I change the opacity of this so I can see how it's aligned with the other layer. And then I try to select this with a 1:1 aspect ratio. So let's see this. Something like this. And then I go to image and I crop it to selection. So now we have these two layers here. So I just increase the opacity again. So we have the silk screen layer, and then we have the front mask layer. And now we just select one layer at a time, make it visible, and export it as a BMP file. So now after exporting the two layers as BMP images, we have to go to KiCad and we have to open the image converter here. And then we need to load in the images one at a time. So here at load source image, we can load our BMPs. And for example, here we can see the front mask layer. So this will be on the front mask. If we go from top to bottom, we can see the output size here. So I just fix it at 50 millimeters. And then here with the thresholds, it's very important to set them properly, because what we see as black color here, that will be part of the PCB design. So for example, if I decrease the threshold too much, then the design will eventually disappear. And in this case, the threshold has to be kept at 100. And we have this checkbox for negative. This has to be unchecked, because if I check it, everything becomes black. So then I would get a black part on the PCB, which I don't want. And then we want to put this graphics on the front solder mask. So I will have to select that. And then I have to save this as a footprint. And then I export it to a folder where I can find it later. And then we go to the next layer, and this is our spaceship. So then I again write it as 50mm times 50mm, and then I have my threshold here. But as I said, the black text or black elements on the picture, what we see in front of us, will become the part of the PCB. And you can see that this is inverted. So I have to check in the negative here, but now everything disappears. And what I have to do actually is that I have to change the threshold here until I actually get something visible. And then I can see that at 88, it's still not visible. But if I go to 86, it's visible. So that's the, let's say, highest threshold which I can use to display all the graphical elements. So I will use this. And then for the layer, I select silk screen on the front side. And again, I save this as a footprint, and I export it to a folder that I know that I can find later on. So then we have these two files, and we can go back to the PCB editor. So here, as I said, we already have all the graphical elements. So actually, I can show you that if I have the front layers, then it looks something like this. But I show you on a separate board how the things work. So as I said, I saved these as a footprint. So we can add the footprint to here. And I have a footprint library, which I just simply call third party. And in that library, I store my third party components. And what we need here is the following. I have the PCBWay rocket front silk. So I import it and put it here. And then I also have the other footprint, the mask itself. So I just put them here. And then I just zoom in and try to align them just roughly, because now I'm just showing you the demonstration. And then I remove their references. And then they are now here. So if I move to the 3D view, we can actually see partially. The reason why just the front silk shows up is because I don't have edge of this board. So I will create an edge, which will actually create the PCB. So we have to select the edge cuts layer and just create a circle. And I created this graphics so it can be, let's say, circled with a 50mm diameter circle. So just roughly put this here, press E, and I change the radius to 25. And then I just move this thing until I can roughly center everything. So this is done. Let's go back to the 3D viewer. And now you can see that the design is there. So it resembles this other design quite well. But you can see one big difference is that on the right side, which is the ready design, that is quite shiny, and this is not shiny at all. And of course, it's because we only have the mask here, but we don't have a copper layer behind it. So what we have to do is we have to add the field zone, and we have to add it on the front copper layer. And then I can just, leave it without a net or add it to the ground layer, it doesn't matter. So I will just add it to the ground layer, and then I just create an area around this thing. And double click, then that's finish. And that finishes the circumference here. And then I press the letter B on my keyboard, and that will fill in the zone, as you can see. So I just undo this. There is no copper, and now there is copper. So I again move to the 3D viewer, and now it's shiny, and that's basically it. So this is how we can make the shiny layer. And the same works with the text. So for example, I want to put a text on it, like I did it on this board, that I put the author and my text on it. We can create a text on the back mask, so actually on the rear side of the PCB. I show all the layers. We move to the bottom copper, put the text here, and then I just enter some text and put it there. So let's say I put it here. And if I check this, there is just the name there, right? And it's not shiny. So what we can do is Control D, duplicate this. You can see that there is another text. I align everything. I press E, and then I put this on the bottom mask layer here. And what this does is that we exposed the metal here. So whatever this text or graphical element will be here, it will have the exposed copper. And then I will show you very soon that when we order the PCB, we can select gold plating for the exposed parts, and I will select that. So whatever text I have it like here in the designer, which has the exposed let's say metal, it will have a golden color. So for example, if we move back, if you see this design here and you see the nice shiny golden color, then that will be in golden color, and actually it will be coated with real gold. So then basically that's it. So now we have the design, and we have to make it somehow possible. So we have to get this design manufactured. And how we do it is that we go here and plot the PCB, and when we are in this plotting menu, I usually save the drill files first, so I generate them. And I have my own folder, so I just generate the map file and generate the drill file. And then once that's done, I plot the PCB, and that will put all the necessary Gerber files in a folder. And then if I open that folder, I have already all those files, and I just actually, what I typically do, you can see the zip file is already here, but I compress them into a zip file, which I can then later on upload to PCBWay's website. So now let me show you how the order process is going. So here we are on PCBWay's website, and I just go to the PCB instant quote. So I open that, and then once we are on this page, we can upload the Gerber files. So I select this upload Gerber files, and then I add it, and then I just select my zip file. So now this will load for a while, but eventually we will see the rendering of my PCB, both sides of it. And as you can see, now it appeared as we wanted. So then what we can do here is, for example, select a bit more. Let's say I want to have 10 pieces. The size is automatically populated because the software behind this, let's say, ordering form automatically fetched it from the Gerber file. And then 2 layers, because we have a front layer and a bottom layer. And then the material is FR4, that's the regular material that we need. We don't need any fancy here. Then we can also select just the default TG, which is actually the glass transition temperature for the glass fiber board. This is fine. And thickness is also fine. We don't want to modify it. And the track spacing can be also the same, and the hole size can be also the same, because I haven't miniaturized anything here, so we can just go with the default sizes. But what is important is that the solder mask, that has to be changed. And now the default color is of course green, but we have to change it to black because that's how the design looks like, if you remember. And I will choose the shiny black in this case, so that is the black. because I want to have that, because the original design was like that. The silk screen, that has to be white, because if you remember, one of the main graphical elements was white. So I leave it as that. And I don't want any UV printing, and I don't want any edge connectors. And then the surface finish is the very important part. If I scroll up a little bit, you can see that there are many like golden colored parts here. If I keep it with HASL with LED, then actually they will be more like silver colored, because that will be like covered with the normal, let's say, coating. But if I use the immersion gold, then it will be actually gold plated, and it will be very nice and shiny. So I select that, and by selecting the gold finish, I can select the thickness of it. I'm not going to torture this board too much, so I can just go with the thinnest one, and that's perfectly fine for this design. And the via process, we can tint the vias. And regarding the finished copper, that is just the thickness of the copper wires on the board or traces. Then I guess just get the thinnest as possible, because we don't have any high currents on the board, so we can go with this. I usually always select the product number. Some people nicely hide it under a big component, but I cannot hide it because I don't have any components, and it's just $1.50, which should not be too much money for anyone, hopefully. So I just select this. And then I will order a stencil as well. There are a few tricks which I want to show you here. The framework means basically you have a frame which looks like a frame of a picture made out of rectangular aluminum profiles, and then your thin stencil is glued on top of this. That is good if you have some kind of fixture that you use, for example, part of a machine, to spread the solder paste with, for example, a machine or just on a semi-industrial case. But we just choose the non-framework, and that will be basically just a sheet of stainless steel where you have the tabs cut out with laser, and you can spread the solder paste manually. So I select that. And since the board has two sides, I just select top and bottom on single stencil. The features have very distinct shapes, so I can select this. And I learned by making a lot of SMD projects that it's better to use 0.1 millimeter or 100 micrometers thin stencils, because then you can actually spread a better amount of solder. Because I have noticed, and some of my viewers also noticed, that sometimes I spread too much solder paste on my boards. And since that time, I always use 0.1, but by default, I've been using 0.12 for quite a long time. So this is it. And then we can save everything to our cart, and it will go through an automatic process where it will be reviewed. And once the board is reviewed, you will get a notification, or you will just get an update in your cart that you can pay for it. And once you pay, PCBWay starts the production, and then you will get your board very soon. So now I just have to wait until the package shows up, and then I can start the assembly. And I will actually show you the assembly in the next video once I get the boards, because mine is also still in production. But in the meantime, don't forget to visit my website for more information and additional content. And also don't forget to visit my PCBWay project page, where I actually shared all the necessary resources for this specific project. So if you want, you can also get this very cool badge. So I hope that this video was useful to you. I hope you learned something, and see you in the next video.